Welcome back to Advent of Code 2019. We're up to day 11. Pretty good progress, I would say, considering I've only done 2 sessions. So yeah, let's do this. Oh, I mean, immediately I saw int code program. Of course, we're gonna build on this. Right, anyway, let's read this. On the way to Jupiter, you're pulled over by the space police. Why is there a YouTube link here? 5-hour video. Okay. Hello, DJ. Not wanting to be sent to space jail, you radio back to the elves on Earth for help. Although it takes almost 3 hours for their reply signal to reach you, they send instructions for how to power up the emergency hull painting robot, and even provide a small int code program that will cause it to paint your ship appropriately. There's just one problem. You don't have an emergency hull painting robot. Funnier about it being 5 hours long, it seems to be from the official EVE Online YouTube. Oh, really? Oh, hang on. Now the link just keeps taking me to this. Oh, no, that's a different link.
Son? Dad, are you space? I'm proud of you, son. Dad, are you space? Yes.
This is from Portal 2. Okay, okay. Huh.
Yes, please, space.
Alright, anyway. Thought it was the first one, yeah. I've played it EVE Online a long time ago. I didn't play it for long. I think it was just becoming... It was starting to die out slowly when I tried to get into it, so... seemed like it was really good in its time, but... Hello, Maro. Maro, you're gonna have to catch up on these 2019 problems now that I'm doing it. Okay, so you'll need to build a new emergency hull painting robot. The robot needs to be able to move around on the grid of square panels on the side of your ship. Detect the color of its current panel and paint its current panel black or white. They start off black. The encode program will serve as the brain of the robot. The program uses input instructions to access the robot's camera. Provide 0 if the robot is over black wheel or 1 if the robot is over white panel. Okay. Oh, interesting. So we're actually going to use... This is a streaming algorithm, meaning that it doesn't just take an input and spit out an output, but actually you keep inputting to a program and that program keeps giving you an output and you keep doing stuff with that output. So it's just you continuously do stuff. You don't see many streaming problems in these contests, but that's because you need an independent program. But in this case, we've built one over the course of like 4 different problems. 5, I think. So now we actually have a complex program that we don't know what it's going to do because it's so complex. So for all intents and purposes, it is a program we can communicate with. Sorry, streaming is not the correct term. Streaming means something different. Online algorithm is the term. Kind of. Streaming algorithm means you have a continuous stream of data coming in, but you just try to keep up with it. So you get some of the data, you do stuff with it, and you just wait for the next data. But online algorithm is a back and forth process. You're kind of communicating with some black box. It's interesting stuff, and these are algorithms that don't really get tested in these contests much, but they're very important pieces of knowledge. They're just hard to kind of implement as puzzles. All right, so the encode program will serve as the brain of the robot. Oh yeah, and Amaro, you're technically on my leaderboard because when you join my leaderboard, it joins all years. So you're showing up as a big fat 0 right now. So all the more motivation for you to. Most people are though. It's an old year, and not many people actually did this year. It looks like this year has a lot of assembly code programming, which is a lot of people don't like those types of problems, and I still don't know whether I like them or not. It's like I always dread them when they come up, but then when I do them, I actually kind of find they're actually pretty original and sometimes pretty smart. Oops. Where was I? So you use input you provide an input to the robot. 0 if you're on a black, 1 if you're on a white. And then the program will do its thing. We don't care what it does. All we do care is that it gives us an answer. It will output a value indicating the color to paint the panel the robot is over. Okay. It will output a value indicating the direction the robot should turn. 0 means it should turn left. 1, it should turn right. Okay. After the robot turns, it should always move forward exactly 1 panel. The robot starts facing up. So far, straightforward. Okay. It's an infinite grid, is it? This is an interesting coffee. It's mushroom and ginseng coffee. Ginseng is like that root that is known to be an aphrodisiac, well, said to be an aphrodisiac, I think. And mushroom is, well, mushroom. Just spilled some on my leg and now I've just burnt my knee. That sounds honestly terrible. I mean, the mushrooms we get in the UK or European countries in general, it would probably taste terrible, but I mean, here in Asia, the mushrooms are so much more varied in their tastes that it's quite plausible you could have any kind of taste that would work from mushrooms. I mean, you have kombucha, which is literally fungus tea. And that's pretty good. I used to make kombucha. Pretty easy to make as well. Like, the fungus just replicates itself so many times that you end up with too much fungus and you start giving it away to all your neighbors and friends and stuff. Okay, so this is not important. This is just describing the example. Yeah. Okay. Before you deploy the robot, you should probably have an estimate of the area it will cover. Specifically, you will need to know the number of panels it paints at least once, regardless of color. In the example above, the robot painted 6 panels at least once. Yeah. Alright. Pretty straightforward problem. I can imagine people will get tripped up on this problem because they will be tempted to initialize a grid, but they don't know how wide to initialize it to begin with. The key is to use hash maps, not two-dimensional grids, really. Then you only store the values that ever get accessed, and everything else is just not stored in memory. I've seen several of these problems, and I remember the forums were full of people like, what do? I can't initialize a grid of 1,000,000 by 1,000,000. There's too many. That's the beauty of hash maps. Hash maps are 90% of the time when people run into programming issues, the answer is actually hash maps. That's not even an exaggeration. And that's not just in these problems, that's in real life software engineering. All right. So we're on to 11. Nearly halfway. And I mean, this one looks like an easy problem, but okay, we've always got part 2 to worry about. Did I copy the whole thing? Yeah, okay. So we're reusing our ink code from here. It just gets bigger and bigger, doesn't it? At some point, we're going to have to make this a Python module. Should we do that? Yeah, let's do that. Let's just make a separate module for ink code. This is the first time I've ever had to do this for a for Advent of Code, but just, I mean, we'll just make a new file here called int code. Just move it in there. In fact, let's take the time to actually clean this up so we don't have to initialize queues and stuff outside of the int code. It's all going to be wrapped up in a class. So we can literally do int code input, int code get output, like that. So we're going to have a class. Let's call it int code. That's not... What's the... Oh yeah, you do it like that. Okay. So in the class, we're going to do this initialization. So this is going to have to import queue. This is going to clean up our codes a lot, because then like 80% of the code will be removed. You'll just import this module here. Import queue. That's all we need for the initialization. And then no, this isn't quite right. We need how did we do it in problem, what was it? 7? Yeah, 7. We created a amplifier, so that's the machine. We created a queue. And then we called next, next, next to get each output. How did we initialize them again? Run in code. Got it. All right, so dot program equals self.run in code on the queue. We're gonna need to supply a program. So we supply a program as a list, and that program is going to get converted to a hash map so that it's infinite size. Okay. No, the program should be internal to the this function. We don't need this. Let's not call it program then. Program is a piece of code. Let's call it machine, automata. What? I just call it machine. I can't think of no. What is the correct thing to call this thing? Robot. Well, in the context of the problem, no, because there's already a robot, and this robot is actually moving around and painting stuff. So this thing here is not a robot. Alright, we'll call it automaton. Just to be technical. I think automaton is probably a good word for this. That reminds me of the point and click game Siberia. It's just a running joke in that game that you have this robot called Oscar following you everywhere, but he hates it when people call him robot. He always corrects them saying he's an automata. Incidentally, my favorite point and click game. All of this stuff is fine. Alright, so there's only two methods which will get called from outside the program. One is add input, put input. And all we do is put X on the queue. And we do get output. And we just do return next of self.automaton. So this code will just run concurrently, and whenever it hits an input, but it hasn't been provided one, it will just stop. So it only runs as much as it can, and then it just pauses and it waits for us to provide the next input. No, sorry, other way around. It waits for us to request an output. It's like a functional program, so until we actually request an output, it just pauses. We request an output, it outputs, and then continues code until it hits the next output statement. Using the inputs that we've plopped on the queue. If it tries to request an input, but you haven't provided one in advance, then it's going to infinite halt. So that's a situation which shouldn't ever happen. We could even catch it as an error. Just to make it really secure. Where do I get the queue? Oh, I need to change all the instances of queue to self.queue and self.p. Yeah. We're gonna have to go through this line by line to be absolutely sure. All right. No. P is a local variable. It's fine. Q is external. So I've only accessed Q like once, I think. There we are. Yield. Wait, no. That's outputting. Inputting is here, q.get. So that's going to be self.q.get. So that's the only place we input, and that's the only place we output. I think that will actually error out, so we don't need to write our own error code. We'll get the Q error code, it'll be clear. If there's no input. Alright, so put input, get output. So now, all we have to do is import int code. How do you do this? From int code. Okay, so if we fetch our program, let's see how we did it for 9. We just basically do that. Okay, so int code equals int code. So we need a program, which is this program. That's it. So basically that is replicating all of that. That's our code is going to be so much shorter. All right, so just check that it runs. Yeah, okay. I'm actually not sure what the behavior of q.get will be. Oh, it waits. It actually waits until there is something on the queue. So it's concurrent. Interesting. Oh, that's what we want. Okay. So then we don't have to worry about providing the input before running the program. The moment we pop something on the queue, it will continue execution. Oh, that's amazing. Okay, fine. All right, so now let's do the actual problem. So we've been given okay, so squares equals default dict int so it initializes to 0 for every cell. The robot, let's say the position is 0, 0. We'll do x. We use x and y cardinal coordinates because we're not actually dealing with a grid here, so we might as well. Okay, so direction equals 0, 1, looking up. We need to just describe what it's like to go left. So left equals, it's going to be a map, which maps 0, 1, 2, minus 1, 0. You can use matrices for this, but too lazy to do that. Minus 1, 0, 2, 0, minus 1. Actually, let's do the matrix approach just for a bit of practice. So how does it work? If you rotate a vector to the left, you actually return... So you actually change direction equals... it's... minus direction, so it's minus the y value followed by the x value. Does that work? All right, so 0, 1 goes to negative 1, 0. So 0, 1. That works for that. Okay, so negative 1, 0 goes to 0, negative 1. Yeah. All right, I think that's it. And right would be, I guess it should be this way around, right? Like you can express it in terms of sines and cosines, but 90 degrees is just a quick check. So 0, 1 would go to 1, 0. Yeah, okay. All right, so we can define forward as well. It's going to be... Wait, no, we're not. The pause is going to be... So it's going to be pause 0 plus direction 0, pause 1 plus direction 1. All right, so that's left, right, forward. Anything else? Okay, so all right, so to actually run the program, painted equals set. So we're just gonna just check all the cells that we've painted. Doesn't matter whether they're black or white. We don't even really need to record. Anything really. Okay, so So how do we do this? We need to just now while true. What's the first step? It's coming up. So the first instruction we provide is just 0. So it starts on a black. So we provide. So we look at where. So we need two things. We need no, we've already got squares. So while true. Int code dot put input. So it's going to be a 0 if or a 1 if squares of the current pos. It's 1, else 0. Or you can actually no, we'll do it like that. And so then we request an output. So the first output will be the color to paint the panel it's standing on. So we do that. So squares pos equals encode dot get output. And then the next output will be direction it should turn. So so it's left, right if it's 1. And then regardless of whether we paint it or not, we do painted dot add pos. And then we move forward. Now this is going to infinite loop. Let's just print length of painted so that we see what the final. So we get a stop iteration error. I mean, that's probably the answer. I don't really know how to handle that. Like, how do we actually stop? Okay, so the first encode should have a boolean self dot is finished. It's false. Self dot is finished equals false. So we should actually do while not encode dot is finished. And I'll do the same thing. How do we actually finish? We want to... So here... It's if we hit 99, isn't it? The only graceful finish is if we hit 99, so that means just do this. That's it. So we won't try to request an output, so we won't get any error, right? Oh, we do. We still attempted to do that. While not is finished. Did it ever reach 99? Done. Oh, it's a timing thing. So we put an input here. It actually hits 99 after we did this. Alright, so our options are either we do this, we just have to make sure we check if it's finished before you request the output. You shouldn't need to do that manually though, you would think. How else would we do it? I mean, you could... Well, if we're doing a while loop, so there must be some break logic, so we should have to do it this way, really. Yeah, so... but you would think... Alright, I don't know, do it like this. If not in code dot it's finished. Hang on. What did they say would actually be the finishing point? Like what actually happens with the robot? It will halt when it's finished drawing, so it's like we provided an input but it doesn't give any output back. Fine. Okay. So we do that. And then do that. So that should bool object is not callable. One? Painted equals set, painted dot add pause. Wait, but the length of painted was changing. Oh my god, that's the wrong way around. If int code is finished. Done. Yeah, but why is it still throwing an error? We tried to call output. Oh, I see. This can't be done as an atomic operation, so I think what we actually have to do is always check if it's none. I don't know what the correct way to do this like cleanly is, but I suppose we can so it basically, if we try to get an output, we should just return none if there's none left. If self dot automaton dot I don't know what any of these methods do. Close running if it's not running. Let's have a look. Right, have a quick search. Python check if generator is finished. All right, we are actually supposed to use hatch logic, I think. So you do try hatch wait, no, there's no except do that. Then we would have to I mean, I've got the answer sitting in front of me, but I'm just trying to make this actually just, you know, like production safe. O equals... if O is not none, if O is none, break. I guess that's how you do it. You get a none the moment it's finished. It's unavoidable. "1951. We don't need to print done anymore. Yeah. Program terminated successfully. Let's do that. And if it didn't, then it would actually give us the opcode, so it's actually telling us what the problem is. Alright. 1951. Alright. Just opening YouTube as well for the chat in case anyone actually drops a message in YouTube. Part 2. You're not sure what it's trying to paint, but it's definitely not a registration identifier. The space police are getting impatient. Checking your external ship cameras again, you notice a white panel marked emergency hull painting robot starting panel. The rest of the panels are still black, but it looks like the robot was expecting us to start on a white panel, not a black one. Based on the space law space brochure that the space police attached to one of your windows, the valid registration identifier is always 8 capital letters. After starting the robot on a single white panel instead, what registration identifier does it paint on your hull? Okay. So that seems alright. Part 2. Let's wrap this up as a method. Just basically all of that, right? Okay. So we want to reset the program, so just say, well, okay, let's take that up here. So painted is an empty set again. Just reset everything. Squares, pause, direction are all reset. They're all reset. Int code is reset. I mean, but we want to set squares. The initial square is white. Didn't use. Oh yeah, I did use squares. That should actually come after. We could have got it wrong for part 1. But we got lucky that it ended up on a square it had actually already been to before. Oh, what's going on here? That should actually be afterwards. We only paint if it tells us to paint. So do we still get 1951? Yeah, okay. Program. So that's confusing. Call it int code. Alright, so now we reset everything. We put 1 here, painted, set, encode, program. And then just run the robot again. Just make sure that it runs. Okay, it does. So now we have the answer staring at us in the face, but we need to actually visualize it because we need to see what those capital letters are. First of all, we need to know the dimensions here. So, min x equals the minimum of S0 for S in squares. We have to do this for all of them. Max x equals max of S0. And then we want the y's. Min y is the... Okay, the IDE is running really slowly right now. Whoops. All right. It's really slowly. Why does it do this? But I've been noticing this happening with PyCharm. It doesn't say it's archiving anything. Indexing. So now we know the bounds. We need to do... We need to make a new matrix. Matrix equals empty list. So for y in range, so we'll start from the top and come down. So we do from max y to min y minus 1 minus 1. Row equals just do a string. Just do, okay, row equals, so it's going to be what should we say? So it's, they said black, white on black. So the best... So rho equals okay, we'll do a hash for white, so it's gonna be hash if squares x y is 1, else empty space for x in range min x max x plus 1. Okay. So that's our matrix. Now let's just print it. For row in map print dot join row. Alright, let's see what this looks like. God, how it's not easy to read that. Okay. So lean back and squint. HKJ. Let me write this down. HK JBAHCR. There's no way that could be wrong. Or they could make it so that it spells a different word if it starts on 0. Well, we tried this before and then it didn't do anything. We could try it again for this problem. So if we just make a mistake that someone might be likely to make, such as set that to 0 instead of 1, what do you get? No, nothing discernible. I was hoping it would spell a message out and then people try that and are extremely confused as how it could possibly be wrong because it does actually spell a word out. That'd be great. You should have done that. It's a trap. There's a nice problem. Nice and easy. So that's day 11. That took me an hour? Really? Wait. Oh, well, I guess I was cleaning up my int code, so yeah. The actual logic for 11 didn't take too long, but it was a good idea to modularize this int code. Okay. Alright, try another one. What's this? 12. Alright. The n-body problem. Uh-oh. This is gonna be physics. Looks a bit physicsy. Oh my. Kinetic energy vectors. Oh man. Okay. The space near Jupiter is not a very safe place. You need to be careful of the big distracting red spot. Big red spot. Persistent high pressure region in the atmosphere of Jupiter. Interesting. Extreme radiation. And a whole lot of moons. How many moons does Jupiter have? This is a list of the moons. Hegemon, is that a Pokemon? These could all be Pokemon. Kale. Meme. Alright. You decide to start by tracking the 4 largest moons, Io. Oh yeah, I've heard of Io. Europa, Ganymede, and Callisto. I've heard of Callisto. Oh, what video game used that? Callisto. After a brief scan, you calculate the position of each moon. You just need to simulate their motion so you can avoid them. Each moon has a 3-dimensional... blah, 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 okay. The XYZ... velocity of each moon starts at 0. Simulate the motion of the moons in time steps. Within each time step, first update the velocity of every moon by applying gravity. Ah, so they're not going in a straight line. They are in stable orbit, I guess. Or it may not even be stable orbit. We just apply gravity. Fine. Gravity is a force towards a point. So we're going to have to calculate the vector towards that point and add the gravitational strength as a vector. Then once all the moon's velocities have been updated, update the position of every moon by applying velocity. Okay. And that's one time step. Okay, I can do that so far. So apply gravity. Consider every pair of moons. Oh, it's gravity applied between every pair of moons because that is how gravity works. Is it going to be follow the inverse square law? No. It's following this crazy exactly +1 or -1 law. Man, what would the universe be like if that was the law? I can't even imagine. That would be crazy. Doesn't matter how far you are from something, it doesn't matter how big that thing is, it exerts +1 or -1 on you. The universe wouldn't even make sense. It would just collapse. Like that can't even be interpreted as as a universe. So they each get pulled towards each other in both x and y by 1. Okay, that's easy to code. Easier than applying the inverse square law. Gravity. It's the weakest force in the universe. The strongest force is electromagnetic. And then in between you've got 2 forces, strong and weak. I guess strong is stronger than weak. Alright, I understand how gravity works. That's not how gravity works, but I understand how this version of gravity works. Then velocity is easy, yeah. It might help to calculate the total energy in the system. Total energy for a single moon is its potential energy multiplied by its kinetic energy. Potential energy is the sum of the absolute values of its x, y, and z coordinates. So is there something special about 0? Is 0 Jupiter? Okay, fine. Otherwise, it doesn't make sense. Normally, potential energy, you only think of it in terms of differences, because there's no, it's all relative, right? Well, potential energy at some point, like I could argue this cup has potential energy now because it could fall down to the ground. But wait, what if I dug a hole below the ground? Now it would fall a greater distance, so it has a greater potential energy. But why did digging the hole increase its potential energy? Well, it didn't. There's no such thing as potential energy, there's only potential energy difference between the cup in this state and when the cup is on the ground versus down in the hole. Okay, whatever, they're doing crazy universal laws here. We'll go with it. A moon's kinetic energy is the sum of the absolute values of its velocity coordinates. That's also very weird. Fine. I think it's real kinetic energy is like half times the mass times the velocity squared or something. The norm of the velocity. Below each line shows the calculation pot. Okay, yeah, I get it. I get all this. It's a lot of example here. What is the total energy in the system after simulating the moons given in your scan for 1,000 steps? Okay, it's actually it's going to scare a lot of people. Well, that's it. Just 4 moons. So all pairs of moons is what, 6? 6 pairs. It's not many. They could have given us 100. Well, okay, there's a part 2 coming, so 1,000 steps as well. So we're going for basically it'll be like 6,000. Still seems like they could have given us more moons. They did say we're only sticking to 4 moons. Okay. Do we actually parse the input? I'm too lazy to do that. We'll just hardcode them. See, if I was doing this live in December, I probably would parse the inputs so that I could make a nice Git page with all my codes, and they run on the inputs so that people can actually run them on their own inputs. But we're not doing it live, so I don't care. Go away, ink code. We don't want to see you again. You'll probably see it for the next problem. So what have we got? So we got moons. So let's say pause or okay, x's equals x is a vector, let's say. So x is, I know it might be confusing x, y, z, but x, I mean the vector x, y, z. Yeah, just go with it. So let's just write them out. So it's 808. 808. 0 minus 5 minus 10. 1610 minus 5. 19 minus 10 minus 7. B's equals what did they say? It starts with no velocity? Yeah. So that's the two variables that are going to be changing. So let's make a bunch of methods just to make this more functional. Then it'll be easier to debug and stuff. So the first method we want is to apply gravity. This is actually the most complex one. So what's the cleanest way to do this then? Hang on, let me have a look at this description again. So gravity has to be applied simultaneously, because otherwise it would matter which order you look at the pairs, right? So we've got to build up a delta continuously and then apply the delta at the end. So deltas equals, so it's going to have to be, so it's going to be like zero, 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 four. So this is the deltas. So for every pair, so we want for V1, hang on. Based on their positions. So for x1 in XS, or x2 in X's, for x2 in X's, oops, there's a siren going on outside. That's annoying. I'll just keep talking, I guess. Okay, we don't want to do this. We want, well, X's enumerate. X's J x2 enumerate x's. Because they could be in the same place. If I is j, continue. Alright, so we'll hit, for a given pair of moons, we will hit that pair twice. So, but that's fine, because we only want to see what the effect is on x1. We don't care about the moon at x2. Alright, so that'll make this easier. So, we look at the vector to get from x1 to x2. So diff equals, it's going to be so it'll be like x2k minus x1 k, or k in range 3. So that's the difference vector. So for example, if we're at 3 and they're at 8 in the x value, we want to add 1. So the difference vector will give us +5. So we want to translate that to a +1, basically. We don't have a sine function in Python, let's just make one. I'm running out of variables here, let's just sine of u. If u equals 0, turn 0, and if u greater than 0, turn 1, else return -1. Let's do that. So we could actually just do that. Sine of that. And that will be added to our deltas. And we just accumulate all those deltas, I suppose. In fact, we could just do this. For k in range 3, deltas k plus equal this. Just do away with that. No. Deltas I k. So it's the ith moon, and then we're just doing the kth. In MATLAB, you could use MATLAB to add vectors together properly, but whatever. Ik. And we don't worry about j, because j will be addressed again when we visit it the other way around. So that should update the velocities. No, it wouldn't, because we didn't actually update the velocities. All we did was we accumulated deltas. Now, so basically, for I in range 4, Vs I equals should we create a we should really create a vector sum, vector addition, all this stuff. Should we do that? And then I could put it here and here, and I probably need it in several places. Yeah, let's do that. So we need a class vector. It's going to be like this. We could make this a data class. I think this will work as a data class. So we've got x, which is an int, got y, which is an int, z, which is an int. Fine, we want to add two vectors. Or maybe it's even defined already, I don't know. Let's test this out. X, so b, don't want to use v, use w equals vector 1, 2, 3. U equals vector 2, 3, 7, whatever. Print w plus u. Does it automatically define this stuff? No, we do have to define it. Makes sense. It doesn't know what to do with that. Doesn't know the order or anything. Okay. Fine. So it's going to be add. Turn a new vector. So it's going to be self.x plus other.x, self.y plus other.y, self.z plus other.z. Similarly, we can do subtraction. So this is minus, minus, minus. What else would we need? That's all for now. So x's equals vector. All right, we'll call them yeah, we'll call them x's. Is the usually the proper term that you use in like linear algebra. So that. Okay. Now let's use all this stuff. So deltas is going to be vector 0, 0, 0. Okay, so for that. So we want to do deltas I equals deltas I plus, we need a sign. So we can do x2 minus x1. But we need to do a sign. So that gives us a vector. And we want to make it have a sign method. So it's going to be... use this sign, essentially. Like that. So this deltas is just going to be dealt what it was before plus that, and then signed into a 1 or a -1 or a 0. Does that look okay for now? Alright, no complaints. So that's gravity. What's next? So that was the hardest one out of the way. Now we apply velocity. So just call it movement. This one's easy. For I in range 4. X's I equals whatever it was before plus whatever its velocity is. Okay, so that's done gravity, we've done movement. Is that it? So after 1,000 steps, let's test this out. Or in range 1,000, like gravity, movement. So after all this happens, I want to see what they look, where their positions and their velocities are. Their velocities are 0. Why is that? It's because they're collapsing on each other. That's actually what you expect, isn't it? They're all sucking each other in. Except it's not, because they're actually asking us for the kinetic energy. Total energy. Potential energy multiplied by its kinetic energy. I mean, that sort of makes sense. Wait. No. This doesn't make sense. Their positions are not equal. Their velocities never changed to begin with, did they? So it starts off as zeros. Did I ever change the velocities? No, I didn't. I forgot to do that. Wow. Alright, so we got the deltas. And now we just update the deltas, right? So we just do this. Vs equals Vs plus deltas. Like that. Alright, now I'll do it. Okay. Next thing is we need to be able to put compute the absolute value sum of absolute values for a vector, because that's just what is used repeatedly. Okay, so when we have done this, we want the total energy for a single moon is its potential energy multiplied its kinetic energy. So energy equals so we're going to sum the total energies for each moon. So the total energy for a moon, it's going to be this times this, where I in range 4. So this is going to be the position. So this is going to be the x's I dot abs sum of abs. This is going to be the v's. Energy 12490. Correct. Nice. All this drifting around in space makes you wonder about the nature of the universe. Does history really repeat itself? You're curious whether the moons will ever return to a previous state. Determine the number of steps that must occur before all of the moon's positions and volatiles exactly match a previous point in time. For example, the first example above takes 2772 steps before they exactly match a previous point in time. It eventually returns to the initial state. Okay. So, I assume... Oh, wow. Wow, okay, that's a lot. Set of initial positions takes this many steps before it repeats the previous state. Oh man. So does it get into some... I'm guessing I'm guessing it's reached some sort of stable orbit. A weird definition of orbit here, but it's an orbit where each moon individually has its own cycle. So we should just find like, I don't know, for one moon what its cycle is. So for each moon, we want to find the start of a cycle, and the period of the cycle, but it doesn't, if we find one whole cycle, it doesn't necessarily mean it will follow that same cycle again next time, because other things might change, so it hasn't necessarily reached its permanent cycle. I'm not sure. We can test this out. Turn something on. So it's kind of well known that the three-body problem is a very hard problem to solve, and we're kind of doing a four-body problem here. So and that's with proper gravity, but here we're using, I don't even know if this is simpler or harder than real gravity. Harder, because it's continuous. Real gravity is continuous, of course. So, sorry, real gravity is harder. Right, so if we're assuming okay. So we're definitely going to need a couple more things in our vector. We're going to need equality to test if two vectors are equal. Oh, no. I think it's already, it knows how to do this. We don't need to do that for data classes. It just tests whether X, Y, and Z are all equal. But that's because this is frozen. We need to make it frozen. How do we do that? It's not frozen by default. Frozen equals true. That means we can check if two vectors are equal. Because X and Y, Z will never change. Right, we might be lucky. Maybe they'll... Maybe the first time they return to a past position is already the start of the cycle. So... Alright, let's do this. Init x's init vs. Alright. So part 1. Xs equals init xs copied vs equals init vs copied. All right. Part 2. So define get cycle. Let's say for a given I, where I is 1, 2, or 3, where 0, 1, or 2. No. Yeah. I is the moon index. So if we're only focused on moon 1, we run the n-body problem, and we try to identify the point at which the moon cycles. When we do that, we spit out the point at which the cycle starts and the period. Okay. I'm just eating what I'm thinking. Oh, this always confuses me. I have a feeling we're going to end up using the Chinese remainder theorem or something. Right, test this out. So, x's equals is equals, so we initialize everything. For t in count infinitely, what are they asking exactly? How many steps it takes to reach the first state that exactly matches the previous state? We're starting at state 0. So that should count as well. So so a state is going to be the position and the velocity. So we're going to have to create a new variable here called, let's say, history. And this is a dictionary which maps all the times at which it was at every state. So that will let us know when we actually revisit a state. So we map states to times. So we say state equals excess. So it's going to be the tuple excess I vs I. If state in history. Then the cycle length is going to be whatever t is now minus history, the historical, the last time we were at that state. And the time will be, sorry, so time equals history state. The cycle is t minus time. And we return time cycle. So that's when we find that repeated state, that's when we return the time in the cycle. So from that time, it will cycle indefinitely. And we could also return the actual cycle. We don't need it. Because they didn't ask us what the state will be. Thank goodness they didn't. Okay. So if it's not in history, then we add it to history. Then we apply gravity, we apply movement, and then we continue. Okay. So let's test this out. Print get cycle for the first moon. It's gonna in my infinite loop. What? Okay, that can't be right. Its date in history. So T is 1. I don't know. Did the state not change? Would have done something weird with these. Didn't change. Gravity. Should that not be changing the excess? Maybe it's something weird about local variables and global variables. Okay, it probably makes more sense to do this. Right, stop. Okay, let's see if we get something out of this. Just leave it a while. Man, how long is it going to take? If it takes too long to even find one moon cycle, then I have no idea how to proceed. Because this is the n-body problem. Like, what are you supposed to do? Okay, it does look like it's taking too long then. No. Yeah, it's taking too long. That was my only idea. Now what? Ah. I'm separating it the wrong way. We should not be thinking about looking at the moons. We should be thinking about the dimensions individually, because what happens in the X plane is completely independent of what happens in the Y plane. It's 3 independent problems. Ah, well, that's something that we can improve. I kind of want to stop. As you can see, I'm eating a lot. That's because I'm hungry and I want to actually go eat. I might be close. Alright, so my idea is, instead of doing it as a 3D thing, just handle each dimension separately. So to do that, we just need to not use vectors, really. So gravity will not apply like this. Instead, it will be gravity in the X, Y, or Z plane. Alright, let's try this then. So essentially scrap the vector class. It was nice while it lasted. Alright, so here's what we do. X's is actually going to be only the X's. It'll be 8, 0, 16, 19. Y's is 0, minus 5, 10, minus 10. Z's is 8, minus 10, minus 5, minus 7. Right. Gravity we take positions and velocities vectors. So say posers and bells. And just make this a scalar process. So delta so given a set of positions of the moons and velocities of the moons in the x direction only, x axis, we want to return the new velocities. All right, so deltas equals 0. You can actually do this. It's safe to do this. Okay, so do this as before. Fine, go to continue. So deltas I basically plus equal x2 minus x1 sine of x2 minus x1, just a scalar sign given this method up here. And when that's all done, the velocities will be changed in place. Should we just call them PS and VS? I don't like trying to write those words. Okay. So PS, oops. VS plus equal delta I. Yeah. And then movement is just be PS plus equal VS. So here we've got PS equals okay, so now we just do x's, y's, z's, for I am range 1000, we do this. Gravity well, we would need VXS, I guess. That's an ugly variable. So we do gravity, X's and VX's. And repeat it for Y and Z. And then same for the movements. Well, the IDE is slowing down so much. And then energy will just be so it'll be abs of x is I plus abs of y's I plus abs of z's I. Alright, it's a bit wordy, but this is for the benefit of part 2. And here we just put a V, V, V. Now, let's see if we get the same result. Vector, where are we trying to call vector? Yeah, we're not using that anymore. PSI is a tuple. Movement vs. Who's using movement? Oh, of course. Huh? Oh, of course. Whatever, just make this a list. I wanted to keep those fixed, but we can do that. Okay, 1249, no, same result. It's actually less elegant now. But it's equally efficient. But anyway, part 2 is where it matters. So get cycle is kind of similar to what it was before. Wait, was 1249 the right answer? Yeah, it was. Okay. Get cycle or one plane. So get cycle for given p's and given v's, I guess. So we just do this. So it'll be, so we take tuple of the p's, tuple the v's. We should probably make them tuples, to be honest. Don't want to go back and change it. State is what the p's and the v's look like. If it's in the history, that history state equals t. Then we do gravity applied to p's and v's, movement applied to p's and v's, and then print. So we just choose one dimension, x, let's say. X's, initialize the x's, the velocities, and now do get cycle of x's and vx's. All right, now we're going to get somewhere. Zero 84032. Interesting. And it was instant. See, I split it up the wrong way. It's not, and I mean, you wouldn't expect a moon to really follow a cycle along the way that we were doing it before, because yeah, this is the way to do it. X, Y, Z are independent. These are horrible variable names. Okay. Okay. Luckily, they all start from they all cycle from the initial state. How nice. So nice. So nice of Eric Westall to give us that. Because otherwise we have to use the Chinese remainder theorem or something. So, so just say cycle 1, cycle x even, equals that. Cycle y equals that. We just need to know the cycle length. Cycle z equals that. So we print the, it's going to be the lowest common multiple. That's when the Kythius, welcome in. What's the aim of the part 2? Finding when moons have completed one cycle in each dimension? That's the trick. The original question was find when the moons have completed a cycle in 3D space. So if you split it up into X, Y, Z, then they're completely independent planes. But each, in X, it has a different cycle length to Y and Z, so they don't line up. So they only line up in some massive number that's too big to compute. But if you can find the individual cycles, which we found. So in the X plane, it cycles every 84,032 Y and Z accordingly. So if we know the independent cycles and we know that they don't affect each other, and because of this the weird physics behind this, they don't affect each other, but in real life they would. But we're not in real life. You can just find the lowest common multiple of those three numbers, and that should be the cycle. You don't just multiply them because they have a common factor. Clearly they have a common factor of 2, but they probably have a bigger common factor than that. So you have to use LCM, which just finds the lowest common multiple. So it's going to be math.LCM CX CY CZ. To import math. It's that big number there. So yeah, if you were just to run it in 3D space, just doing X, Y, Z every step, it would take that many steps before they all line up again. I mean, this kind of problem has appeared several times in Advent of Code. Eric likes to do this kind of problem where you have one massive cycle, but you have to figure out a way to split it up. So there's always some sort of way of finding an independent frame and then breaking it down into those independent frames. It's just I went about it the wrong way to begin with. I was trying to split it up by moons, but that doesn't make sense because moons affect each other. So moons are not independent. Because the whole point of this is gravity. If one moon does a cycle, that doesn't mean it'll do the same cycle the next cycle, because all the other moons could be in different places. So moons are not independent. They are very, very dependent. But X, Y, and Z are independent simply because he defined it in this obscure way. Oh, well, let's see if it's the right answer. Gravity. Now we just need the interstellar music to play. Yay, it's correct. You would think it would be correct, because if we even got a cycle in the first place, that it should probably be correct. Otherwise there's like a near zero chance of finding a cycle if we were doing it wrong. Yeah, that was a good problem. He was quite generous as well, because he had them all return to the very initial state. He could have been mean and had the cycle start from at some point the moons follow some weird path, but then eventually they reach a cycle. That could be the general case. And if the three moons reach their cycles at different points, then it's not as simple as just finding the lowest common multiple of the cycle lengths. You have to account for the different offsets as well. which would need... Which, is this the way you use Chinese remainder theorem? No, I don't think so. Chinese remainder theorem is solving something much stronger, much more complex. No, we don't use Chinese remainder theorem. Chinese remainder theorem is something way more complex. Oh no! It is. This is a Chinese remainder theorem problem. He didn't say they will return to the original state. So if you were to just solve the problem without actually looking at the numbers you get, you would have to use Chinese remainder theorem. Like if you're solving the most general case as he's written it, then yeah, you need to use this. And I don't really remember how to use this. It came up once in Advent of Code, but I think he sort of realized that people were a bit thrown off by it because this is kind of advanced stuff. So since then, all the problems he's usually started the offset to be 0 or the same for each element, so that you don't need to do this. I can't even remember that. Like the theorem it's not constructive, so it doesn't actually tell you what you do as such. It just says that if a solution exists, then it must satisfy this rule here. And then it's up to you to do what you can with that information, but my maths ends at A level, and this is far outside my comfort zone. Yeah, I don't know if you ever did any BMO or IMO, but I think a lot of schools participated in the BMO, British Maths Olympiad. But that did actually use Chinese remainder theorem. I didn't do it myself, but they gave us the test anyway, and people who qualified got invited to the camps and stuff. But so yeah, that level did use Chinese remainder theorem amongst some other things like modulo arithmetic and stuff, but it was never covered in school because it's not. You need to know group theory, but it is covered in undergraduate mathematics. But this idea of doing the LCM, like without using Chinese remainder theorem, I think it did come up in A-level maths, but probably the further maths modules, like the more proof based, because the base maths A-level is what it has, like a bunch of statistics and mechanics modules, and then there's like pure 1, which covers like differentiation and integration. But then the further maths and additional further maths, which I did, not many people even bothered to go that far, but cover all sorts of interesting. They actually cover some basic programming as well, but not programming, but algorithms programming. So basically running programs by hand without ever writing any code. Let's have a look at how fast people solved that. What day are we on? 12. Interesting. People actually found that one easier than the previous one, so there was an increase in solutions here. Actually, not really. Well, the ratio of golds to silver is lower, so technically it was harder. What was 11? Oh, it was this. Oh, it was the int code thing. Yeah, that makes sense. That int code 11 relies on you having solved 9. 9 relies on you having solved 7. 7 relied on you having solved 5. So that's the pattern. Every odd number, they're going to give us an int code. And you have to use the same code that you're building up each time. So we could take a sneak peek at 13. Oh, of course. Yeah, it does. That's the pattern. Yikes. This must have been a unique year then, because he stopped doing that. He stopped having problems rely heavily on previous problems. They still do sometimes, but not... You might have like 3 problems across the month where they rely on the previous one. But here it seems like it's every odd number, which might have been too much for people. Because they don't like, I guess people don't like the idea that if you get stuck on a problem and you can't solve it, then you're basically not able to solve a bunch of later problems too. Everyone wants a fresh start on the next day in December. Okay, well, we're basically halfway there, but it only gets harder from now on. Some of these problems could take several hours each, if even that, sometimes longer. What was the other thing I wanted to check? Leaderboard. Yeah. Alright, I'll finish there then. Alright, that's 11 and 12 done. It's clearly I'm slowing down because it was only 2 problems this stream. So from now on, I bet it's going to be 1 problem per stream. But almost finished all past problems. There's just 2021 to do. And then I'll be up to date. I'll have the coveted 450 stars. Okay. All right. Thanks for watching. See you in probably tomorrow or the day after for more Advent of Code. Bye-bye.